Um, Today we are going to complete the discussion on Bayesian learning of Bayes networks, which is sort of mentioned in passing last time, and also talk about the learning in the context of hidden data, hidden variables, which is EM algorithm. Okay. And I also sent the last homework. It's only 3 problems, one on RL and one on Bayes networks, which basically you would have completed by today's thing, and then one extra problem, try to show that if you add links to the Bayes network, the likelihood can never reduce. Okay, that's basically an issue in structured learning, for example. Okay. So we talked about ML, right? Likelihood-based, maximum likelihood-based learning last time, and then we looked at both the discrete case and the discrete case, single parameter, discrete case, multi-parameter, and the steps were, of course, you write down the expression for the likelihood, you write down the derivatives or the partial derivatives with respect to the parameters, and you essentially maximize. I mean, you equate the derivatives to 0. Or in essence, actually, what you're trying to do is find the maximum of the likelihood function. And one way of doing that is take the derivatives and equate it to 0, and then find where they become 0, and that will give you the parameter values. In general, the likelihood, for the Bayes nets, we notice that things are particularly simple because if you have normal multinomial CPTs, multinomial CPTs basically means that you have tabular conditional probabilities. Okay, in that case, basically parameters don't entangle, so each partial derivative would be about one parameter, and then they'll all be linear, and so you equate it to 0, and then you can solve a set of linear equations, and you're done. In the case of continuous, we also looked at continuous case, and we found here still the parameters entangle, except it turned out in this particular case that you got 2 simultaneous equations, except one of the equations is about only one of the variables. The second equation is about both the variables. So it's again easy to solve. Okay, and we looked at that. So it looked like that's the basic idea of ML learning, and you should remember these are the steps in doing ML-based learning, and it becomes particularly simple for Bayes networks. Now the question, of course, is what's wrong with likelihood-based learning? We remember that likelihood-based learning was the simplification of the right type of learning, which is Bayesian learning. And to remind ourselves, the problem is the likelihood essentially assumes there is no prior whatsoever. So it's basically assuming that all hypotheses are created equal. So, for example, as this is a way of remembering it. If I tell you that a particular tag came heads up, once in 3 times, versus 1 million times in 3 million times, they're both equally. They're basically equivalent information from a likelihood point of view. Okay, whereas you would like to think that this is much more stronger evidence that the probability is 1/3, whereas this is probably it's just too it's too small a data, and maybe it's not 1/3 probability. Okay, now if it's not 1/3 probability, what else can it be? If you don't go with the data, what else will you go with? That's where you go with the prior over the hypothesis. Okay, so you essentially have, before you even started tossing the coin or tossing the tag, you have a prior. Now if it's a flat prior, then essentially, if you don't know anything about what happens to thumb tags when you toss them, then you have a flat prior. If on the other hand, you actually think you know what happens when a coin is tossed, then you have a more peaked prior saying the theta is always closer to half. Okay, and then the data can override it. It can push you towards a different direction. Okay, so basically to do this, then you have to keep track of the prior, and then you update the prior to get the posterior on the hypothesis, which is what we talked about previously. which is what we talked about in that candy example. The thing about the candy example was the number of hypotheses were discrete. There were only 5 different hypotheses. In these kinds of scenarios, you have continuous parameter. So you have a continuum of hypotheses. Okay, so keeping track of a continuum of hypotheses, the picture that we saw, where is that picture? The picture that we saw multiple times, it's not even easy to draw. This picture, right? This one here, each curve corresponds to one hypothesis, right? Each curve corresponds to the likelihood of one hypothesis as the data kept increasing. Since there are only 5 hypotheses, then you only have 5 curves. If you have a continuum of hypotheses, then this isn't a pretty picture, right? So the basic idea, the technical problem, see, there's nothing conceptually hard about Bayesian learning. It's all technical problems, okay? So technically what you need to deal with is, you need to essentially deal with a way of representing the prior over the parameters, and you need to update the prior over the parameters. Okay, so if theta is the probability for this particular problem, let's say if you assume that theta is the probability that the coin comes heads, then each different value of theta is a different hypothesis. Since it's a probability number, it will be between 0 and 1. But every continuum value between 0 and 1 is a different hypothesis. Okay, so the P of H, the hypothesis prior, is essentially the P over theta. I mean, it's a distribution over theta values. Okay, the distribution over theta values. So then starting with the prior on theta, we just need to compute the posterior. That's what you always do. Okay, so you look at the data to compute the posterior, and then once you have the posterior, you predict the data. So you let the entire hypothesis space tell what the classification for the new data would be, and then you take a weighted average in terms of the posterior. Okay, so that's what happens in Bayesian learning. So the challenge, of course, is finding a distribution over continuous space such that first it can be represented compactly. Okay, remember, unlike discrete distributions, continuous distributions, you cannot, if you want to represent continuous distributions, you need to have parameterized distributions. For a discrete distribution, you can always say, I'll take a table. Okay, you have a k different values for this variable, I'll just take the probabilities that this variable takes each of these values. For continuous distribution, you can't do that because there is no table that can keep track of all the values. Okay, so you have to have a parametric distribution. The tricky part is you start with a parametric distribution, right? And then you update with the data, update with the evidence, and the new parametric distribution, there is no reason why it should be in the same form as the original distribution. Do you see what I'm saying? Okay, so suppose I came up with some simple distribution like this, right? And then I updated it, and it became like this. Now, this could be a normal distribution. This cannot be a normal distribution. Okay, so now you would need, so basically every time you update the distribution, you will get a, especially in the case of continuous scenarios. This is not a problem. This is not a problem you would see in the tabular case, because you had a table of values, you had another table of values. Right? You don't see any difference. But when you're dealing with continuous quantities, you have to deal with parametric distributions, and a technical issue would be whether the distribution would retain its shape when you update it. Okay, how many of you have heard of Kalman filtering? Okay, so we could have talked about it in this class, but I didn't get a chance to do it. But Kalman filtering is, the reason Kalman filtering is so celebrated is basically, it so happens that if you have a normal distribution and you update the normal distribution on the beliefs, if your beliefs distribution, belief state is a normal distribution, and your observations are conditional normal distributions, then the posterior will also be a normal distribution. Okay, so what that means is Kalman filters are extremely easy to implement. They just have to remember the parameters for this Gaussian and the parameters for the conditional Gaussian with respect to the observations, and then you'll get a new parameters for the new Gaussian. Now, most of the time in the world, actually, the belief space distribution, initial belief space distribution is not Gaussian. And the observations given state are not also Gaussian. So Kalman filtering assumptions don't actually work. But people use the Kalman filtering assumptions most of the time and try to get by. And when it actually doesn't work, in fact, for those of you who heard of Kalman filters, you may also have heard of particle filters. And what particle filters do is they essentially do a tabular representation of a continuous distribution. So they approximate a continuous distribution by keeping samples of it at different places. Okay, and then they update this distribution. You take the same number of samples and then you propagate it and you get a new tabular new sample distribution. Okay. That is what happens in the particle filters. Okay, so right now, let's come back to our case. We will try first to see if it is possible to find distributions that will keep their shape. Okay, and for every kind of a likelihood function, there are distributions. For certain kinds of likelihood functions, there are distributions called conjugate distributions, which have the property that if your original prior is in conjugate distribution form, then you multiply it with the likelihood, you get a new, the posterior, which will also be in the conjugate distribution form. It's similarly like normal distribution with a conditional Gaussian distribution gives you another normal distribution. That's what Kalman filtering was doing, right? So if you have a conjugate prior, then you can essentially, they have the property essentially that you multiply the prior by the likelihood, you'll get the posterior, which will also be in the same parametric form with just slightly different parameters. Okay, in the case of Kalman filters, it's not the case that this normal and this normal are the same exact distribution. It is that it's a normal distribution with a slightly different mu and sigma. Okay, there are many distributions in the world which will never be normal, even if you try to come up with different mu and sigmas. For example, any bimodal distribution, it's dead on arrival, right? Because it cannot be a normal distribution at all. Okay, so we make a big deal in Bayesian learning about conjugate priors. But you have to understand the reason for that is technical. It's not so much that you really should have, it's not really the case that your background knowledge is always best expressed in the form of the conjugate prior. It is that if you can somehow express it in the form of the conjugate prior, then your life would be simple. Similarly, in a Kalman filters, it's not the case that your knowledge about the belief space distribution is always a normal distribution. But if you can somehow find the closest normal, then your life would be simple because you can then get another normal, an update. But at some point of time, those assumptions start failing, and then you would need particle filters. And similarly, even in the Bayesian learning, today we'll mostly talk about conjugate priors, but really, in certain cases, your prior may not be expressible in any conjugate distribution. In which case, you have to bite the bullet and actually update the prior, which keep changing its thing. So, for example, you will wind up having to do these kinds of particle-based representations. Okay, but for today, we will assume conjugate distributions. Now, what is a conjugate distribution for us? So you could, for example, have tried theta, the prior on the theta, you could think of it as a uniform distribution because you don't know anything about theta, right? It's between 0 and 1. I don't know which value it is. All values are equally likely. So I can assume it's a uniform distribution. Now, the problem with the uniform distribution is right after you see the data, it's no longer uniform distribution. Okay, so instead there is a generalized version of uniform distribution called beta distribution, such that uniform distribution is a special case of the beta distribution. And then, you stay in beta distribution. If you start with beta distribution, then you will always stay in beta distribution. Okay, so here are the beta distribution. A beta distribution is defined like this. So beta is given, has two hyperparameters A and B, and over theta is alpha times theta power A minus 1, 1 minus theta power B minus 1. And as you keep changing A and B, the distribution changes. Now what is this alpha? The alpha should be a constant such that the area under the curve sums to 1. Okay, now it turns out that alpha is a, I think a gamma function of some sort, and we won't even, look at it right now. Okay, in fact, I think the text actually gives the exact values for the alpha. And the alpha value depends on the A and B, obviously. Okay, but the interesting thing is, if you were to consider beta distribution for different hyperparameter values, it looks like this. Here is beta 1, 1. Okay, and this is beta 2, 2, and this is beta 5, 5. So basically, as you will get, so this way essentially beta 1, 1 is what you thought. Originally you assumed that the theta is pretty much anywhere. But after, let's say, you looked at a million coin tosses, you got 500,000 heads and 500,000 tails, you would start winding up with a beta distribution. I mean, I'm jumping ahead, but essentially the posterior will also be a beta distribution, and it will be more peaked. If you increase A and B values, the distribution becomes more peaked. If you increase one of their values while keeping the other constant, the mode changes. So for example, this is a case where, so this is beta 3, 1, this is beta 6, 2, this is beta 30, 10. Okay, so notice that 6, 2, okay, so this is 6, 2 is basically 3, 1, right? And this is 30, 10. So these two have the same relation to each other as these two. In the sense, the mode is approximately in the same place, but it's peaked. Okay, and okay, so that's the thing about beta distribution. So now suppose I use that distribution to specify my prior. Then what's interesting about it? Suppose if I start with my prior to be A and B, I mean beta AB, okay, and then I've seen now posterior, of course, is the prior times the likelihood, right? Suppose I've just seen the first data point, which is a cherry candy, right? So actually it should not be cherry candy, it should be heads and tails. This I copied it differently. Okay, so suppose this, what am I doing in this case? I'm doing A plus 1. So I saw heads. Okay, then what I would do is this. Remember, the possibility that I'll get heads is theta. Okay, so I would say theta times the original prior distribution, which is beta A B theta. That's what this is asking us to do. It will be essentially a different normalizing constant times theta power A minus 1 times 1 minus theta power B minus 1. This the different constant here is because beta itself has its own constant. And I have another normalizing constant here. So I'll have one normalizing constant, I'll find it as a detail. Okay? And then this is theta times theta power A minus 1, 1 minus theta power B minus 1. The nice thing about this is these two will become theta power A and 1 minus theta power B minus 1. Right? That's basically in the same form as the original beta distribution, except with the hyperparameters A plus 1 and B. Okay, so basically that way, by doing this, the math works out correct. So you just have, you see one extra set of heads, so you want your prior to take that into account, and the way the prior is going to take that into account is it changes the beta's hyperparameter such that these A's and B's, you can actually think of, in this scenario, A and B, you can think of these almost as, before you saw this data point, you have seen A heads and B tails. And this data point adds, if it's one more head, then it adds +1 to A and leaves B alone. And clearly, if the A and B are large to begin with, so this problem of the ML was not differentiating between 1 head out of 3 tosses and 1 million heads out of 3 million tosses. Okay, you can differentiate it here because a million and plus 1th head after having seen 3 million tosses, that would be A and B such that A plus B equal to 3 million. And now you're going to change A by just +1. So the distribution doesn't change that much if you look at the way these things are going. Whereas if A and B were small to begin with, then one value can change, have a bigger impact. But neither of them are going to suddenly make this distribution be they're not becoming an impulse distributions. Okay, you're not committing to one particular value like ML does. Okay, so that's basically what you would do in the case of our Bayesian learning for just coin tossing example, or just one parameter candy example. Okay, so the conjugate distribution that you use here is the beta distribution. It turns out that the other kind of distributions that you care about, in Bayes networks, what other distributions do you care about? You have binomial. Now the interesting thing is, it's conjugate to what? It turns out that binomial distributions conjugate is beta distribution. So if your likelihood is binomial distribution, and if you multiply that by beta distribution, you get another beta distribution. Okay, so for the Boolean variables, then distribution is binomial. And so the specific value, the distribution over the theta for the binomial has to be beta distribution. Okay, so that's one type of distribution we might care about. What other distribution would you care about in Bayes networks? So for example, I can have a Bayes network, here, this one is a Boolean value, and then the theta is affecting this. That's what we saw right now. More generally, you have a multi-valued variable. And the theta of that, and basically the prior on that is all the different values. So for example, if you have a variable which can take values v1, v2, v3, then essentially you have 3 parameters, theta 1, theta 2, theta 3. And they can all be varied while keeping theta 1 plus theta 2 plus theta 3 equal to 1. Okay, so then you need some sort of a generalization of the beta distribution. Okay, this is basically, this is called the multinomial distribution. Because it's almost the same as binomial. Just theta 1 power the number of instances of v1 you saw, theta 2 power the number of instances of v2 you saw, theta 3 power the number of instances of v3 you saw will be the likelihood. Right? And what you need is, you need that likelihood when multiplied with the prior should still be in the same form as the prior. Okay, that is called the Dirichlet distribution. Okay, so you keep hearing about Dirichlet everywhere, these days, and that's basically because Dirichlet distribution is the conjugate for the multinomial distribution. Okay, so that's what this whole slide is saying. A prior distribution family PC is considered a conjugate prior for a likelihood function family PL. If starting with the hypothesis prior PC1 from PC and seeing data with likelihood PL from PL, the posterior hypothesis will also be in the class PC. It will have different parameters, but it will be in the same class. Okay, and beta distributions are conjugates for Bernoulli or binomial likelihood distributions. Dirichlet are conjugate for multinomial. And then if in fact you have a continuous distribution here, it's a normal distribution, then there is a conjugate distribution for normal distribution called normal Bayesian distributions, which have the exact same property. If you multiply them by the normal distribution, you'll get still a normal distribution. Okay? So that's basically, and so once you have the conjugate distributions, then you know that the technical problem of maintaining the posterior has been made easy. The maintaining posterior, you just maintain the posterior by keeping track of the new hyperparameters for the conjugate distribution. Okay? Now, what happens when you actually need to, so what does Bayesian prediction do? So suppose you have started with a beta AB as the prior, then the probability of heads at that point would be A by A plus B. The most likely probability of heads would be A by A plus B. Okay? Now, I'm sorry, wait, no. So the expected value, which is basically the mean of the beta distribution. Okay? So, if your prior is beta AB and you have not yet seen the first coin being tossed and you are asked to predict whether it will come heads or tails, okay, based on your prior you would say the expected value would be A by A plus B, probability for heads. So if the heads is like 1 and tails is 0, then the expected value of the next toss would be A by A plus B, which is the same as the mean of this beta distribution. Okay. Now, actually, how did I get this? To get this, I need to basically compute the expected value with respect to the beta distribution. So I need to compute P heads given theta times P theta d theta. That integral has to be computed, and it is an ugly looking integral. I mean, especially if you have forgotten integration by parts and fun stuff like that. Okay, but if you do that, after half a page of integration by parts, you will get A by A plus B as the answer, which is kind of good, right? Now, after seeing DH heads and DT tails, the posterior will now be A plus DH, A plus DH, and B plus DT. I mean, it's easy for us to say that because we kind of figured out that's exactly how the prior posterior is changing. Okay. Now, any beta with this kind of a posterior will have a mean, A plus DH by A plus DH plus B plus DT as the mean. That would be your prediction about the next toss. Now, I'm saying this, it's easy for me to say this because I have, once I did this expectation, once I actually computed the integral once, the next time around I just keep using it because that's what, for any beta distribution with AB as the hyperparameters, the expected value will be A by A plus B. Okay, and this is again, what we were hoping. The hard parts of Bayesian learning are updating the posterior on the hypothesis and using this entire family of hypotheses to predict the next value. Both become easy because of the conjugate prior. Okay? So that's why people at some point of time stop thinking that it was put there mostly for a computational convenience and start thinking that conjugate priors are somehow required for Bayesian learning. That's not true. It just makes your life simple if you can, somehow express your background knowledge in the closest conjugate prior that you can find. Okay, and also the other interesting thing is that I mentioned this previously, that Bayesian learning, what Bayesian learning does is what Laplacian smoothing does without any theory for naive-Bayes classifications. When normally in naive-Bayes classifiers you add a number to the denominator and the numerator, right? And so in fact here you notice that if you don't have Bayesian, you will get dh by dh plus dt as the most likely prediction for the next toss. And instead you added a on the top and then added a and a b in the bottom. Okay, that almost looks like what Laplacian smoothing does, and Laplacian regularization does. But the reason that is reasonable is, in some sense, you can think of that as by doing that, it's sort of getting the same, some of the same effect as the Bayesian learning, by not being completely stuck with the data. Acting as if you have seen some prior data before you see the first data. Questions? Yes?
If you have exponential function instead of like beta or normal function, you do the same. The point is, we usually do not consider like memory for exponential function. So
I mean, you're talking about exponential family distributions?
Yes.
Uh-huh.
So here, for example, when we are talking about coins, so as long as we have more number of heads and tails, then we have like a new posterior function, so we update. But when we are talking about like a exponential function, that like number of errors or number of fails in like in electrical tools, something like that, then doesn't matter how many fails we saw in the past, still we consider the same function. I'm not sure if I mixed something or not, but I'm just wondering, can we use the same idea even if we have like exponential function as a prior function?
Of the likelihood function?
Yes.
Okay, no, basically in general Bayes learning is easy for exponential family distributions because there are known conjugate priors for all of them. Okay, now the issue that you are asking maybe, so all the conjugate prior does is make sure that when you multiply the likelihood by the prior, what you get would be in the same form. That's all. Okay, I think the question you are bringing might be a different issue, which is you are somehow saying, I want to say that prior evidence should not have any bearing on what happens next. Now, if that is the case, in some sense, learning is kind of an iffy situation, right? If the number of failures before have no bearing, nothing you have seen in the past has any bearing on future, then you should not be doing any learning. So some parts of your parameters, some properties of the data from the past should be affected, that you have seen in the past should be affecting what you will see in the future. It may well be the case, for example, that the color of the coin has nothing to do with whether or not it will come heads or tails. But that's a different issue. That's like, it basically means color is an irrelevant variable, so it should not be, somebody who modeled the Bayes network to begin with, if they put irrelevant variables in the Bayes network, then that problem might come. But if nothing I have seen in the past will allow me to guess what will happen in the future, then there is no learning. Okay, we could talk offline.
Okay, sure.
Okay, so now in the case of Bayes net scenario, I showed this to you last time itself, but so this one we basically, whatever I did here is for a simple Bayes network. It's also a Bayes network. It's a simple Bayes network where a theta parameter was affecting a single node Bayes network. Right? And so already you notice that normally if you just looked at, write me a Bayes network for the coin toss example, you would write coin toss, okay, and then you would put a prior on the coming heads theta, coming tails 1 minus theta, right? That's what you would have said. Now what I'm saying is the theta itself is a variable in your network, and so that's why the Bayes network you actually looked at has the data here and the theta here. And I know that's kind of snuggled in, snuck in. You did not notice it. It becomes more obvious when we see the general Bayes network scenario. For example, a case where you have both the wrapper and the flavor. Okay, so the flavor itself has some distribution, but the flavor determines the wrapper probabilistically. right? So in this case, basically what happens is, so if you want to just do it all in terms of Bayes network inference for a minute, then each example, this example, flavor and wrapper, now this example is going to be determined by the theta values. Okay. There is a theta which determines the flavor being lime, and so the 1 minus theta would be the cherry, or vice versa. And then these is theta 1 and theta 2 are extra parameters that determine the wrapper being red when the flavor is lime, wrapper being red when the flavor is cherry. So you have 3 parameters. Okay, so just like I had previously theta determining this data, now I have to have essentially 3 theta, theta 1, theta 2, theta 3 are now part of the network. Now in general what you need is to provide a prior on theta 1, theta 2, theta 3. And the way you do it is to provide the joint distribution over theta 1, theta 2, theta 3. Right? Okay, but mostly people make an assumption that, one reasonable assumption you will make is that parameters are independent. It's not, there is no good reason to believe that they are dependent, so you assume they are independent. In which case, essentially, there is no link, there is no direct links between the parameters themselves. There is no direct links between the parameters themselves, prior-wise. Okay, but notice that the parameters do become dependent on each other given the data. Okay, as you see, for example, as soon as, before these guys were there, these three were independent. But now this data connects all of these guys. So there are dependencies, induced dependencies between the parameters. If you remember deseparation from the Bayes network lectures, Bayes network discussions from previous classes, because we didn't do it here. Okay, so that's your, now you have a network after having seen the one data. Okay, so now the interesting thing is that before this came, you had just a Bayes network with theta 1, theta 2, theta 3, theta 1, theta 2. Okay, so there is a prior, and you can use that prior to basically do your guess as to what would be the flavor and wrapper for the next candy. Now this candy came along. You've seen evidence. So now your network looks like this. So now actually, now I know a flavor of this guy, and the first data points flavor and the first data points wrapper I know now. That means these two are evidence nodes. Here is a Bayes network, I have 2 evidence nodes. I can compute the posterior using any Bayes network inference algorithm on these 3. Since they are, and you compute the posterior, okay, that would be the new hypothesis posterior. Okay, when you get one more data, you put that into. Now I have a bigger network. Once again, I have all these nodes are evidence. I just compute the posterior on this. See, this computation of posterior is basically doing the inference using the Bayes network inference techniques, which for complete data until now, as part of learning, we didn't have to do inference. That's going to change in a minute, even for ML, even for maximum likelihood, it turns out you'll have to do inference as part of learning. But until now, until this slide, you never seen inference being needed. Until Bayesian learning, you never seen inference being needed to do the learning. But since there is no learning actually in Bayes learning, right, because it's just updating the posterior of the parameters, and then using that to compute the expected value of the next data point. That's what you're doing. Okay, so that's what you do. So from a Bayes network point of view, you just basically keep recomputing the posterior and using that to, so if you say that there's a new data point is going to come, I want to guess what their flavor and wrapper should be, then I'll put, let's say, I could have put this here, and I say these are the evidences. Then I could have just asked what would be the values of, what's the posterior on these. which in essence involves finding the posteriors on these and then marginalizing over them, and then basically predicting this. Okay, so that's basically what happens in Bayes learning. Okay, on the network structures. Okay, so each example is inserted into the Bayes network as evidence, and the posterior over parameters is queried. The wrench in the works is that the size of the network grows with examples, and we have continuous quantities. Okay, now this discussion I have done till now does not care about what the distribution, what priors are you using for theta 1, theta 2, and theta. Because you have a good Bayes network inference engine, you just ask it to compute the posterior. Now, if in fact you are using conjugate priors like Dirichlet prior and so on, that computation would be very simple. Okay? So we will assume normally that these guys will have Dirichlet priors for all the parameters, because these are all multinomial distributions. Binomial is just a special case of multinomial. So Dirichlet is a general case of beta distribution. Okay. And then, notice that we just happily made an independence assertion because that would work and that would help us. Okay. In general, again, the thing about Bayes network, as I mentioned earlier, is it can be quite intractable if in fact there is no easy way of keeping track of the distribution over the hypothesis, or doing the integral over the hypothesis. The expected value involves an integral. Okay, and doing the integral. Okay, and integral is basically inference in the Bayes network scenario. Okay. Any questions? Yeah.
Sorry, what's CPD stand for?
Conditional probability distribution. Yeah. Or density, conditional probability density. Yeah. And it's been used CPD or CPT, conditional probability table. But in general, the T means it has to be a table. Okay, but it can be arbitrary parameterized distributions. All this is a conditional probability density. Right? So for example, if one of these is a continuous variable, this is a continuous variable, this is a continuous variable, then this guy will need to have a conditional Gaussian or something. It can't have a table of probabilities. Okay. One interesting thing I hope you're realizing is that, I think starting about POM-DPs, we went from discrete world to the continuous world, because certain cases you start having to deal with continuous quantities, and there are interesting technical issues with that. Conceptually, there is no difference. Okay, conceptually you just change the integral with a summation with an integral. That's all. But if you're trying to do exact computation, it becomes a pretty hard situation. Pretty tricky thing with continuous quantities. Now, things like particle filters change the integral back into a summation. Right, because you're doing it with respect to some samples. Actually, the interesting part of particle filters, I haven't gotten into, since I mentioned it, I'll say it, that normally what happens if you're not careful is if you have like a distribution with samples and then you update, then what might happen is the new distribution would look like this. Okay, everything else, basically what you realized is that when you're sampling, you're sort of sampling with this in the beginning like a uniform number of samples across the distribution, let's say. But then as the posterior comes, posterior might have made the continuous distribution look more like this. In which case you only have one good guy, taking care of this whole area. And all these other guys are out of circulation because they're just basically looking at the parts of the belief space which have close to zero probability. So you think I have 1,000 samples, I should be doing something good. But 999 samples are doing nothing. So sample efficiency is out the window. And what particle filters do is they reweight the samples such that you in essence push the samples to the high likelihood regions. That's the interesting part of that one, but we will not talk about that. Okay, and you will sort of have to do this in the Bayes networks too if you don't have a good conjugate prior and you have some sort of a sample-based prior, then it better be the case that the samples are tracking the high probability regions as the data comes through. So in fact, there's a very nice connection between Kalman filters and what's happening in the Bayesian learning. Okay. Okay, so it's been a while since we actually thought about logic, but in general, prior knowledge is a bigger deal. It's always known to be important in learning. Having background knowledge is something that's we expect is important. We can't learn new stuff unless you already know something before. This is why, I think I have mentioned this, if not I'll mention it again, that this is why you don't just keep teaching POM-DPs to elementary school kids with 10,000 repetitions and hope that they'll get it. Okay? Instead, you will make them go through multiple different classes, and then when they have enough of a background knowledge, then you give a few examples of POM-DP lecture and hope that they got it. Okay? In fact, there is this thing about human learning that you don't learn anything that you don't already almost know. Okay? That's about prior knowledge. You need prior knowledge. And so what's interesting is, in some sense, in the statistical learning scenario, the priors are the only way you bring in prior knowledge. Okay. Since we are not really talking about logical learning in this class, I'll give you an example that will make you think about how that is also useful in logical learning. For example, this is my favorite example, and it's also in the textbook, I think, somewhere. Sao Paulo airport example. So you got down in Sao Paulo airport, okay, and the first person you saw, by the way, Sao Paulo is in Brazil, okay. The first person you saw was wearing red shirt, green pants, yellow glasses, and was speaking Portuguese. Okay. Now you have only one data point. Okay. Here are some hypotheses. All Brazilians wear red shirts. Another hypothesis: all Brazilians wear green shirt, pants. And the third hypothesis is they all wear yellow glasses. The fourth hypothesis is that they all speak Portuguese. All of them, from the maximum likelihood perspective, they're all equally valid. You saw one data point, it all has those probabilities, so actually all Brazilians must be doing this. And yet we laugh at people who make the first three hypotheses and think that fourth hypothesis is somehow much more reasonable. Why? Not because you knew what Brazilians speak. I mean, some people probably know what Brazilians speak. Okay, in fact, Brazil is an odd man out, right? Because in the entire Latin America, in fact, in the big country that does not speak Spanish is Brazil. Okay, so in some sense, most people don't know that they don't speak Spanish; they speak Portuguese. But what you do know is that nationality determines language. Typically, you also know that nationality does not typically determine the color of clothes people wear. Nationality does not typically determine the color of glasses people wear. Okay, so that's your prior knowledge. It was sitting there waiting for one example to come, and one example came, you can plug it into, since nationality approximately determines the language, and this guy seems to be a local speaking Portuguese, I would assume all Brazilians speak Portuguese. Now, of course, this is not to say that you cannot make errors. You could actually, might find another, American expat trying to, catch the flight back and is speaking English, so you think all Brazilians speak English. Okay, it's just that you are much less likely to, you are more, at least if you do that, then you are, in some sense, people understand your error more than if you thought all Brazilians wear red shirts and green pants. Because we assume reasonable priors. Okay? And in general, background knowledge and having the background knowledge being specified and handled during learning is a big deal. It's an important thing, and then Bayesian learning allows that. Map learning also allows that. Map learning allows, provides you a way to penalize the highly complex hypothesis. So that's the way it allows that. Okay. Any questions? Okay, so now let's do some application, and then that sort of leads us into EM and hidden data business. Okay. So suppose we have a relational table in some database table. Okay. So let's say an employee table giving the age, position, salary, etc. of each of the employees. Okay. You've seen a bunch of this. This is your training data. The table itself is the training data. Okay. Suppose I want to learn the generative model underlying it, so that I can then generate virtual employees. Right? Okay. How can I do that? One, of course, I need to assume, let's say, that the first thing is if you want to learn a Bayes generative model, you could learn a Bayes network generative model. Okay. Now the first question, of course, is who is giving you the topology of the Bayes network? Okay. To make our life simple, let's assume that all of these are sort of discrete variables. So we are thinking only in terms of discrete variable multinomial distributions on the Bayes network. Okay. So the first question you need is, where do you get the topology? Let's assume somehow we know that. For example, we might know it if you know the domain and you know what things are connected to what things, or if you know some of the causal dependencies in the data, and so you can at least put those edges and then look for the rest of the edges. Okay, that's normally, if you don't know the full structure, then you have an issue of structure learning. We will not get into it for now. Let's assume you have the structure. Now, if the relational table is complete, that means there are no null values in the table. That means every row gives the values for each of its attributes. Okay. Then this is basically learning the parameters of the network using Bayesian learning, Bayes network learning. For complete data case, extremely easy, because all you do is you find the parameters by taking the counts, the ratios of the counts. Okay. That much we are fine. Okay, now this is up to here, it's good, right? So you could learn like a Bayes network for a complete table. If I give you if somehow you got hold of a structured, the topology, which is a big assumption, but let's assume you have that. Now suppose that the table is slightly dirty. What that means is there are tuples that have some missing values for some of the attributes. Okay, actually it's an interesting issue. In fact, as long as it is complete here, it could have been dirty in the sense that some of the employees have wrong ages, some of the employees have wrong salaries, and you won't know any difference. As long as the data is large enough, since you're doing statistical learning, you'll essentially, some of the noise is handled that way. Okay, so here, even if it is dirty, you don't know, because whatever training data you have is the training data you have. Here, the training data advertises on its head, I'm not only dirty, I'm actually missing pieces. So you cannot any longer assume that everything is clean. Okay, so now some of the employee tuples are missing age information, others are missing salary information, etc. That could happen, right? So what can I do? Here is one idea. If only a small percent of the tuples are incomplete, okay, then we can learn the model using just the complete values and the complete rows. That's enough. For example, suppose you have the table is size million, and about 5,000 of them have incompleteness. Then you just throw them out and learn the data, learn the Bayes network from just the rest of the data. Okay, and to the extent this data is representative, you are throwing some small fraction shouldn't have affected the correctness of the model too much. Okay. By the way, while we are talking about this, how do we know whether we learned a good model or not in these kinds of scenarios? How do you know, for example, even in this case, how do I know that my model is reasonable? One idea, of course, again, after all, we are just using ML, maximum likelihood, whatever it said, we are doing it, okay? The question is it doing the reasonable thing, okay, for your data? And one thing you could have done is, if you have a table of this size, you could have held off this part, okay? This data is kept separate, okay? And then you only learned the Bayes network using this part, Okay, and then you can essentially, in some sense, because this is a generative model, the question is, are you able to generate these rows? Now, obviously, you can't exactly generate those rows. What you really want to do is compute the likelihood of this held out portion with respect to this network N1. And suppose your friend used his own separate methodology and came up with network N2, then you can compute the likelihood of this held out part using N2. And whichever gives higher likelihood for the held out part is the better model. Okay, there are other ideas also. Instead of likelihood, you can talk about things like perplexity. Okay, so in some sense, what is it about bad learners? Bad learners don't have a model of the world, and so they are perpetually surprised. Everything is, oh my God, this is what happens. Oh my God, there is a class every week at 12:40. I did not know that. Well, I didn't know it because I came last time, but I forgot. So I don't learn anything. So life is perpetual surprise for bad learners, because they have no model, and so they're always perplexed by the world. Okay, a good learner, on the other hand, knows what is expected to happen, and more or less it happens, and so they are not as often surprised. Right? So it is reasonable to compute the likelihood of the held out part and see which one is giving higher likelihood, and then that's the better one, because they are less perplexed by the held out part of the data. Okay, fine. Now, if in fact somehow this is the way to do it for generative tasks, because this is not a classification task. Normally in a classification task, in all these attributes, some of them are xi's and some of them are yi's, and you're only interested in predicting yi's given xi's. Okay, that from normal machine learning scenario. So in this case too, there will be some yi. Let's say maybe there's one particular thing. Can you predict the salary of this employee? Okay, and everything else is given, and so you can predict it using your network and see how close it is to the actual value. That's what you do in normal learning. But if you want to actually, in a true generative model, you should be able to generate employees which look more or less like these kinds of employees. And so you can ask yourself, how likely are these employees given this network? Okay, so keep that in mind. That is basically likelihood of the held out data. Okay, so now you come back here. So you basically, there's a small portion that has incomplete values. You learn the model using just the complete tuples. Okay, and what's interesting is that, well, you might say that now since I have the model, I can actually complete the dirty tuples, the incomplete tuples. Do you understand what I'm saying? So if I have a big table which tells me, basically car information, let's say, and I have figured out from the table that most of the Accords are manufactured by Honda, and there is this one car which says Honda but doesn't say who manufactured it. You can use this learned knowledge to complete this piece of missing information and say this car also was manufactured by Honda. Okay, so I could do this. I could not only learn the model, I can use the learned model to complete the data. Right? Reasonable thing. Now, actually this is also true here, but in fact, if you completed the data, let me go back here. If you completed this data now you have more complete data. Shouldn't you learn the model again? This is exactly what looks like total circular reasoning, right? So you learned the model based on the clean data, and you predicted the missing values for the remaining data. Now the entire data became complete. Now you become greedy and you say, hey, there's more complete data now, so let me learn again. You might want to think about that. Okay? And now it becomes a bigger issue if a non-trivial percent of the tuples are incomplete. Because here at least you would have thought, well, my model is good enough. Only 500, 5,000 tuples were missing out of million tuples. 5,000 tuples are incomplete out of million tuples. So I don't really want to waste my time relearning the model. But suppose a non-trivial percent of the tuples are actually incomplete. Maybe like, 50% of the tuples are incomplete. Then you learned the model with just the 50% of the complete tuples. Now the temptation, and then you completed the rest. Now the temptation to relearn is much more, overwhelming, right? Because you learned based on just a few clean data, and then you use that to complete the, dirty data. But now there's a lot more dirty data, a lot more clean data now, quote unquote clean, based on your learning. You try to learn again from that. Okay? And if you understand that temptation, in fact, now that we have completed all the incomplete tuples, we have a fully complete data, learn the model with this completed data and see if it's any better. And in general, the way you decide whether a model is any better is if its likelihood for this held out piece increases, for example. And in fact, you can also say, I can do the likelihood of the entire data too. That's also reasonable, because the example data from which you learned is also can be seen as test data, and see what's the likelihood of the data that I have. Okay, this is cleaner thing to do. You kept part of the training data separate, but people don't like to do it in learning because examples are hard to come by. So you don't want to keep it, in a separate drawer. So you just want to try and use most of it. But anyway, so a model is better if it provides higher likelihood for the observed data, and more often than not you'll find, in fact not more often than not, you pretty much always find that when you do this, the likelihood increases. And so in some sense the model is better. Now the question is, why stop here? Right? You basically can now say, I have a complete data, a better complete data from which I learned the model. Okay, then I no longer say, well, previously I completed some of these incomplete data with a wrong model. Now I have a better model. So let me recomplete them and then relearn the model. Do you see what I'm saying? So you are learning, the completion part, when you are completing the data, what are you doing? You have a Bayes network, and you have a tuple which has most of its values known, some values unknown. So you ask the Bayes network, here is the evidence of the tuple, which has A1 is this, A2 is this, A3 is this, A4 is this. Tell me what should A5 and A6 be? And Bayes network will normally give you the posterior on A5 and A6. And that's the inference part. So when you completed the data, you did inference using the learned model. When you took the newly completed data and learned the model again, that is maximum likelihood based estimation of parameters. That's learning. So you're doing learn, infer, learn, infer, learn, infer. When do you stop? When the likelihood no longer increases. And then you stop. This is basically EM. Okay? And in this case, essentially the data is not complete in an easier scenario, in the sense you at least know all the attributes, but some of them don't have values for some of the tuples. But if I continue this example, then I get the true reason for using EM. This is the easy reason for using EM. And the true reason for using EM is essentially, suppose in the previous relational table scenario, we assume that some of the tuples are missing some of the attribute value. This is what we assumed until now. That some of the tuples are missing some of the attribute values. But what if all tuples are missing a particular attribute's value? Okay, so in the case of, for example, in this data that you gave, I gave employee table with age, position, salary, etc. But maybe what I really should have talked about is the educational level of each of the employees. And maybe that's much more predictive of how the data is organized. Because after all, for example, the education level might say something about the salaries, about the kind of jobs you get, etc. Right? So now where did this attribute come from? Completely out of your head. You just made up. So you basically, the interesting thing about this is, you give a data like this, I feel like there's something here too. I feel like something here too. So I just make extra columns. They all correspond to hidden variables. Now, the first question, the two questions are, this is like having an attribute column whose value is not known for any of the tuples. That's the difference between the previous and this case. Previous case, at least some of the tuples had the values for this attribute. So you could use them to learn something about how this attribute, takes values. Here, nobody has them. None of them have them. Okay? Now, basically this is like having an attribute column whose value is not known to any of the tuples. My question is, why would we do it? And can we still use EM to do it? Okay? We'll answer the first question first. Can we use EM to do it? Yes. As crazy as it might seem, you can use EM to do this. Basically, you can put any random values up front in this missing column. Again, I assume that you have this, I assume in this case that you have the topology. So you put the topology in. So I put in some random values in this, initialize this, learn the parameters for that particular Bayes network. Okay, using the learned Bayes network, I recomplete the missing values, the completed values, recomplete the completed values, learn another set of parameters until you stop increasing the likelihood. Okay, the second question is, so there is no reason why we should initialize using complete data. We can initialize the model parameters randomly and still do EM looping, essentially. Okay. The second question is, why would you want to do it? Why would you want to, it's like this Robert Kennedy kind of a thing. Why would you want to think of a world that never was and ask why not? Right? Basically, this is your data, and I'm asking you to learn the structure in this data. And you're saying maybe there is some additional columns, and it's increasing the complexity of your work. But we have talked about this. These hidden nodes can structure the Bayes network such that the number of parameters that you need to learn are significantly lower. Remember the M nodes, N nodes, and all M are connected to all N, except you hypothesize that these M actually affect an intermediate node like the average value or something, which then affects each of these values. In which case you can reduce the number of parameters you learn quite significantly. Okay, it's this promise of learning the structure of the data, unsupervised, because I didn't tell you what the values of these are. There is no supervision on this particular column at all. And when you made up the values for this column, you essentially are doing unsupervised learning. Okay, in particular, suppose the education thing is PhDs and undergrads, then I essentially just in front of your eyes split the data into two clusters, PhD cluster, undergraduate cluster. So, EM is clustering. How many of you heard of k-means? What does k-means do? Exactly this. And in fact, I want you to think of how does what I just tell you and what I'll tell you in the next slide differ from k-means. K-means is connected to EM, but it differs in an interesting way. Okay? So, but why would you do it? Because given a complete relational table, why would you hypothesize? Because the right hypothesis on the hidden attribute can significantly reduce the number of parameters. So for example, the education level of the employee might cluster the employees into PhD folks who presumably have high salaries, interesting positions, and mature ages. Okay? And the non-PhD folks who presumably have low salaries and green behind the ear ages and assembly programming kind of jobs. Right? And so